Welcome to Finite Element Modeling. Today we'll be covering the analysis of a cooling channel in a liquid propellant rocket engine application. However, I want to point out that some simplifications were made so that the heating applies all around the circumference, which is not the case in the real application. However, we're trying to show you how to approach the problem in a practical way to solve the temperature distribution in a cooling channel given the conditions of the hot gas and the cooling fluid inside the channel. So I hope that you find this tutorial useful, and for now I'll turn it to Fadhel, who will walk us through this tutorial. Thank you, Fadhel.
Hello and welcome to this new tutorial about heat transfer in thick-walled cylinder. We'll be doing a very simplified version of regenerative cooling in liquid propellant rocket engines, in which usually within these engines we have the fuel, which is at very low temperatures, a liquid fuel at very low temperature, is passed through a small channels or tubes around the engine chamber to cool it down before injecting that fuel into the chamber. Our problem is simplified as such. We have the tube here that's shown here, and the liquid propellant is passed through this tube here. The surrounding of that tube is the engine chamber, in which we have hot gases and which is subjected to hot gases and hot temperatures, and that's taken care by, and that's described by these values here of the temperatures and heat transfer coefficient. The temperature of the coolant, which will be going inside here at negative 200 degrees Celsius. It's convection heat transfer coefficient. And usually these engines are made of materials such as aluminum, steel, or other metal alloys. And as you can see here, that is subjected to very high temperature. So we want to make sure whether this material, after simulating it, whether it will melt down or not. We have the dimensions of our problem that's described here. We have a radius of around 0.019 meter and a thickness of 0.06. So we have a thickness that's almost 3 times the radius of that tube. In simulating it, we'll be doing it using 2 ways to see that the same problem can be done in 2 ways. We'll be using it using shell elements, in which we're within this problem here, we're at least for this problem, we're not interested in what's happening on the axial direction. We want to see what's happening through the thickness, how the temperature varies through the thickness for this thick cylinder. So one way we'll be doing it as a shell element, and we are assuming that its thickness does not matter. I mean, the axial thickness, that depth value does not matter, and we want to see the temperature variation in this direction. And then we'll do it using another way, using axisymmetric element. And we'll see that how using these 2 ways, we can get the same results. So let's start now. So we'll start by selecting our directory, and it's already selected here. We'll start by renaming our model, and we'll call it thick wall cylinder shell model. And let's say okay, and then let's go to part. Let's call it something similar, thick cylinder, and we'll go to 2D shell, and our dimensions here will be a meter, and we have a radius of 0.019. So let's have something like 0.05 here. And it's a circle, so 0, 0. That's the center point. And the the radius is 0.019, 0.0191, and that's 0. So, and we need to create another circle, for example, the thickness, which will be at its center is 0, 0. And the value here of the thickness is that radius, which is 0.0191 plus this value here, which will be 0.0791. And let's hit enter. And that's how it looks like. So you can tell now the thickness is quite huge. So this is our model here. And now we need to model the material property. We go to material and it's aluminum. And we need to enter its density. And we have the density as 2700. That's the density for aluminum. And we'll need, since we're doing thermal analysis, we'll need conductivity, which for aluminum is 240 as given in the problem. And we'll need the specific heat, which is given at 900 here. So, okay. And the solid section. So usually if we choose a shell element or 2D, within that one, we use a section of solid. And if we go to 3D and we want to model a shell element, we'll go to shell here, shell section. It's quite weird, but yeah. So let's create the section here. And it's green, which means that we're good to go. And let's go to assembly, create, independent. And then let's go to step, create, and let's call it heat transfer. And let's choose heat transfer here. And we want to do a transient problem, transient state. And this problem takes a bit of time. So let's run it at 1000 seconds here. And the initial point, let's have it at 0.02, for example, here. And the minimum value, let's minimize this one to 1 minus 6, for example. Maximum increment, let's have it as 0.2 at 2. You can increase that one as well. And probably we'll need to increase this one a bit, the maximum number of increments. Otherwise, as Abaqus tried to solve the problem, it may run out of the number of increments and will stop and it will abort. And the maximum temperature change, let's have it as 1 here. So the smaller this number, the higher the resolution is, and the longer the simulation time will be. We're done with the step. Let's go to the interaction here. And let's look at our problem. In our problem here, we have the liquid propellants going inside. So that means we have an interaction, a heat convection here that's happening, heat transfer through the convection from the inside due to the liquid propellant. And we have the heat transfer on the outer walls due to the temperature of the chamber. And that's described by this one here. So let's start with the inner walls. So let's go to here. Let's call it inner wall. And let's go to surface film condition here. And let's click continue. And it's asking you to select the surface. And let's select this one here. And and here the film coefficient is, it's 500. It's 600 here, which is the H, the convection heat transfer coefficient. And the sink temperature, which is the temperature of the surrounding now, which is 1000. Oops, down. This is the inner wall. So that should be the H should be 100, and that one should be, the temperature should be negative 250. Okay, and now let's go to the outer walls. Outer wall, and let's do this. And this one now is 600, and the temperature is 1000. And let's click enter. And let's go to load. For the load, we do not have load, but we have an initial temperature. So let's go to quality temperature. And it's in the initial state. So let's go to initial. And here we need to go to other and choose temperature. And that initial temperature is the temperature of the entire tube. And that temperature here in this case is 10. That's our initial temperature. So we're done with this step now. And let's go to mesh. Within the mesh here, as you can see here, it looks, I believe it is pink. So if you remember from our previous simulations, we used to do a structured mesh. And now you can see here, we cannot choose this option. So you can do it either one of two ways. Either use a sweep, which is fine for cylindrical structure, or we can do one thing here so that we turn this into green. And you can go by any of these steps, but essentially I can turn it into green or structured mesh using a very simple way. Let me show you how you do it. So let's go back here to part and just click on the scissor. And since this is a shell, we need to go to face here, and let's click on sketch. And let's draw lines here at this point here. Oops. And line here. 2 more lines and we're good to go. So the structure is very simple to make it structured mesh. So that's why I want to show it. And it's good to see how you can turn these problems into structured mesh, because that reduces complexity and gives you better resolution and with smaller number of elements. So let's go now. So yeah, that's good. And usually when you change the structure or divide it or so, if you choose anything, that might change. So now let's make sure that our selection here is still valid. So let's go to edit. See, it's not valid. So let's reselect it really fast here. It's like this one, this one, this one, and this one here. So that's the inner wall. We're done. Okay, let's do the outer wall. And pick. Let's select this one, and this one. And done. Okay. The field. Oops, no. Let's just make sure that this one is still valid here. I believe it is. Oops, seems not. So let's do this just to make sure. And now let's go to mesh, and let's go to assign mesh control. Select everything here. Done. And choose quadrilateral, and now the structured part is allowable, and we can choose it. So let's do this, create, and now it's green and nice. So let's, before meshing it, let's choose number of elements here, and that's in these values are meters now, since that's what we entered. So let's have it as around 10 millimeter. Let's have it as 5 millimeter. And now let's mesh it. So it looks nice. So usually if mesh, if it looks nice, then that's a good sign. That's kind of an art. So, and the element now, let's choose the element type. That's heat transfer. And let's choose quadratic for this one here. And let's run it. Now we're almost done. Let's create our job, and let's call it. Oops, the name is missing at NH thick wall cylinder shell model. Done. And let's run our sanity check. So history output. Yeah, that would be a good point to do it. Let's do that. Let's go to step. Let's create set points here so that we monitor inner wall, and from geometry, let's select this point here, and let's create another point. Set create. Let's call it outer wall sensor. That looks nicer, sensor. So, and let's go to history output, create inner sensor output, and here let's go to set. Let's choose our inner wall, and let's choose the values that we want. I just want the nodal temperature now, so I'll only choose these here, and done. Oops, I'll create the outer wall as well. So let's create this one here, and let's call it outer wall sensor. Set outer wall, and again I just want to choose the nodal temperature, and we're good to go. Job, right, and let's check. So check is completed. That's good. Let's submit it. Okay, and let's monitor what's happening here. So this process is quite longer process, because we have heat convection that's cooling from inside, and we have a heat input or heating from the outside. So that process takes a bit of time, and usually, unless if you have a sense of a problem on how much time, and that's good to have a sense of the problem, how much time it takes. But in simulation, if you're not sure, that might take a trial and error to choose the right time. And since I've done that before, and probably now 1,000 second will be sufficient to reach the steady state solution for this problem here. And you can see here that we're already in the 500 steps, I mean increments, but the total time is still within the 42 seconds, and that number is supposed to go to 1,000. So you can see, if I believe I set the limit to 2,000. So if that increment limit that I set to 2,000 is reached before this number reached 1,000, then the simulation will abort. If it aborted due to this reason, you can still view the results, but it just means that it reached the limit that you set, and Abaqus stopped that. But you can see the solution up to that point that it stopped at. So I'll pause now, and now you can see the simulation is done, and you can tell I barely made it. So the increment size, I mean, it reached to 1,900, and my limit was 2,000, and so I barely made it. And before going to our results, I just want to highlight one thing here. So my initial increment that I inserted was 0.02, and which is what Abaqus started with here. And you can see here, this one here, it says that attempt 1U, which means that this attempt didn't converge, the solution didn't converge for this step. So Abaqus, what Abaqus needed to do is to start with an even smaller initial step than I suggested. And it went to 0.05. And even within that one did work, and Abaqus then, and you can see it's 2U, and Abaqus need to reduce that step even further. And here you can see the value of the minimum increment size that we set and the initial value. So if you have a good guess of the initial value, that could save time for Abaqus into starting with the right step and solving it right away. So that helps. I just want to make this comment, and now let's go to our results. And let's see the temperature distribution and what we have here initially. And you can see here the temperature distribution that we have. We have a temperature of 950 something at the outer walls, and the inner walls we have 937. And if you want to see the temperature variation across the time, we can go to the history output that we created, and let's go to ODB history output. And this is the inner wall points that we set for the history. And here we can see the temperature. And using this way, we can somehow tell whether we're reaching a steady-state solution or not, because we are saying here the temperature is reaching a value that's now it's kind of steady. It reaches a plateau. That curve reaches a plateau. And yeah, we can now we can tell that we're reaching the approximate, I mean the steady-state solution, and we can plot the inner and outer wall as well, the temperatures and how they vary with time as well. So so I believe that's that's pretty much what we want and what we want to see for the first part. And now what we want to do, we want to create another model but using axisymmetric element, and now see if we can have similar results, and we'll plot them both against each other and see if we have same temperature distribution or not. So let's do that. Let's go back to here, and let's create a new model. So let's create a new model here. Model, okay. And let's call it again, thick wall cylinder. Let's see, symmetric. And let's go to parts. Let's go to axisymmetric here. And within the axisymmetric, we will choose the shell. So let's just go back here to the model for the axisymmetric. What we want to do is kind of, we have excess of symmetry, and we'll create something, and that will create around that, that geometry will be kind of rotated, assumed to be rotated around the axis of symmetry. And now the axis of symmetry that assumes will be the y. And what we're interested more is into the inner walls here, and not into that length. So let's model that. Let's call it thick wall cylinder, and let's keep the same size. Right. So that's our y-axis, and we will create a rectangle, and that rectangle, when it's rotated, that would be the tube. And we're interested to see the temperature variation across the thickness, not across the length. So across the length, we'll assume it's the same. So let's start with and that the distance from y is the symmetric axis, and that distance should be the radius here. So starting point should be 0.0191 and 0. So that's our starting point. Oops. And the second value here should be the value of when we added that one to the thickness, and that one should be 0.0791. And this gave it just a height. That height now it shouldn't make any difference. So let's make it small so that it does not take much within the meshing the number of elements that we do not need. Okay. Let's have it. And now this is the model that we have, in which later when we simulated that should be rotated around that axis, and we're interested in what's happening through the thickness, which is this plane now. And this line here represents the inner wall of the pipe, and this line now represents the outer line, the outer surface of the pipe. And for the materials, to save time, let's go to copy objects here. And since we created that material into the first model, let's go to here, and from model, copy objects again. And here we just choose the materials and apply. And when we go to here, we can see our material. Now let's create a section. And let's call it solid section. And here, this one's not gonna affect. Okay, and let's select it. It's not a green yet. Let's make it green. And now we're good to go. Assembly, independent, create, and let's go to step. Let's hit heat transfer step. Let's call it heat transfer. Enter. And we're doing a transient state again. And let's have a time of 1000 again. And let's have an initial step of 0.02. Let's just have this one as 1 minus 6 as well. Let's have this one as 1. Let's have this one as 1. And here, to be safe, let's put it as, let's say, 2500. And let's reduce one to 0.01. Enter. Interaction. For the interaction here, we have the inner walls, which is this line here, represent the inner wall. And that should be the coolant, which is has heat transfer convection coefficient of 100 and negative 250. Let's just make sure. Yes. And okay. And now the outer wall. Let's choose this one here, enter. And that's 600 and 1000. And let's go to load. We have the initial condition, which is initial temperature at 10 degrees Celsius. Okay, so 10. All right, and let's go to mesh. And I believe we can have a structured mesh right away now. Quadrilateral, structured, nice. And let's have an element size of, that's 1 millimeter. So previously we had 5 millimeter. Let's have 5 millimeter. Well, that's coarse, because now we're having we're having quite different dimensions on that one, that circle. So let's have one. So okay, and let's choose the element type, and it should be heated transfer. And now you can see here that the element type is now 4-node linear axisymmetric element. We're not using the it's an axisymmetric element, and we can choose the quadratic element here as well. So let's try this one here, the quadratic. We choose the element, and we're almost done now. Let's create a job. Let's call it thick wall cylinder axisymmetric. Let's click continue. And let's see if we can get the same result out of both. And let's submit it now. Oh, let's see if we let's take a point for the inner walls and outer walls as well. Set create inner wall. Let's choose this one here now. And let's choose another point for the outer wall. So, wall. Let's choose this one here. And let's create a history. Inner wall sensor. Inner wall, and let's have the nodal temperature, and that's it. Same for the second one. And outer wall, and again nodal temperature. Done. And I believe the output history, the output is good, and let's submit it now. And let's monitor it a bit in the beginning. Let's see what happens. Just a warning. Okay, that's good. So let me pause it for a bit now, and let's come back again. The simulation is done now, and you can see here it actually took quite similar time to the previous one. So this one took around 5 minutes, and for the number of increments, it was more or less quite close to the previous one. And even though I would assume this one will take more time usually, because if you compare the number of elements here for the axisymmetric one, we used 600 elements. For the previous one, we have 720 elements for the shell element. Anyway, let's see our results now. Let's go to results and see if the results match. So let's go to here. And look at this. One thing that you can do here, it's kind of a trick. You can go to, so that you can see it as, to see it as a circle. You can go to I believe options, common maybe. Oh no. Wait a second. Oh yeah, you can go to this one here, ODB display options, and you click on that, and you can go to let's sweep extrude. And if you click on that sweep option here, and you can see it, and we can make it 360 and apply. Oh, not 250, 360. And now let's have our results. Let's compare it with the previous results. And the way to do that, let's create another window just like this, and then let's create on this one. Let's click on this one, I mean. So now let's highlight this window, and we have our previous simulation that we have from the shell model. Let's double click on that, and now let's see, and let's see how it looks. And now this one is the, okay, we should show the temperature, yes. And you can see here the temperatures profile, and we have exactly same temperatures. We have kind of same maximum, same minimum, and we use two different approaches. And you can see here you can reach kind of same results, but with different approaches. But the computational time for each might be a bit different. So let's see if we can plot the ODB results here. So the inner and outer wall for that one. And let's see if we can have same for this one here. We can plot the inner and outer wall. And you can tell here for both, we have exactly same results. But we felt quite different approach with different elements. So with that, I kind of, let's go to our one more thing here. So the temperature that we reached here is 950. And one of the problem statements that we want to see if the material will melt down or not. And the material we're using here is aluminum, and its melting point is somewhere around maybe 600, 700, depending on what type of alloys. But if you have an aluminum, then most possibly that material will melt down, and you either need to reduce that temperature or change material and use a material with higher melting points. Now I end my presentation, and let's go to my main slides here. So again, let's kind of summarize. We were trying to simulate the regenerative cooling in liquid propellant engines, in which we have liquid propellant fluid that's passing through a tube that's cooling the engine, and that's taken care by the effect of taken care by the outside temperature. We simulated that using shell element and using axisymmetric element. We showed that using two methods, we reached to exact same solution. And with that, I end up my presentation. Thank you very much.